Hello guys, so today I'll be explaining the physics AMS of term 1 week 2. Which of the following statements describing the safety measures while using radioactive materials are true? Eating is allowed when handling radioactive resources. Definitely not. Eating, drinking, being exposed to radioactive resources is not an option. So we're not gonna choose this. Then, radioactive sources should be identified using your eyes only. You shouldn't even bring your eyes close, like not even a couple of centimeters close to the radioactive material, because it's very, very dangerous. Radioactivity, what will it do? It will cause a deformation in your cells, which could possibly lead to cancer. So that's why you have to keep it away from your eyes and from exposing it to your body. It is safe to move a radioactive source with your hand? Definitely not. We just said it can cause radiation, which will cause negative effects to your body. And then radioactive sources should be locked up in a safe place. This is true. We have three types of radiation. We have alpha radiation, then we have beta radiation, and we have gamma radiation. Alpha can be stopped by a piece of paper. Gamma can be stopped by a book or anything thick, and beta can be stopped by a book or anything thick, and gamma can be stopped by lead. So here is why they use the example of a lead box, because it can basically stop the three types of radiation. Finally, make sure that the radioactive source is pointing away from you. Yes, this is very true. Because as we said, radioactivity is very dangerous. It can cause your cells to deform and not grow properly, so it can cause cancer, basically. Number 2. Underline the factors that affect the rate of radioactive decay. The two factors, there are only two, I think, that affect the rate of radioactive decay are usually the nature and the quantity of the radioactive factors. So pressure does not matter, position doesn't matter, temperature doesn't matter. None of these, like for example in chemistry you have the pressure will affect the volume and whatnot. These do not affect radioactive energy, no. Only the nature of the radioactive source to determine how radioactive it is, and the quantity, it also determines how radioactive it is. Because the nature, it could be one of the least radioactive to one of the most radioactive, and the quantity, if you have a small quantity, it will give less radiation than if you have a bigger quantity. Okay? So these are the two factors that affect the rate of radioactive decay. Number 3. A radioactive source emits radiation into a space where a downward electric field is present. The source emits beta particles and gamma radiation. 3 detectors A, B, and C are used to detect the radiation. Now here's something to write as a note. Alpha radiation, it is a helium particle, and it is positively charged. Then we have beta, it is an electron, and it is negatively charged. There's another thing we learned last year, but I'm not gonna mention it now so we don't mix up. And finally we have gamma, it's a photon, and it has 0 charge. So if they're telling us something that has a positive charge, will it be attracted to the positive or the negative? Positive will be attracted to the negative. So definitely alpha will go towards the C. Now, if they're telling us something that is negatively charged, then it's gonna go to the opposite charge, which is positive. So definitely beta will go to the A. And something that doesn't have a charge will just continue its path straight. So gamma is this. This is beta here, this is gamma, and this is alpha. So detector A, which is the positively charged, will detect the beta particles, okay? Because positive will attract negative. Then detector B, which is a straight line, okay, there's no positive, no negative, it will catch the gamma radiation. Why? Because the gamma has no charge. And finally, detector C. They told us that the source emits only beta and gamma radiation, so we do not need the alpha right now. So detector C will detect no radiation. Number 4. Drag and drop the pictures to describe the tracks left by different particles in the cloud chamber. Okay, alpha in the cloud chamber, okay, it is a bunch of straight bold lines. So alpha is straight bold lines. Then beta in the cloud chamber is a bunch of dotted kind of zigzag lines. And finally the gamma, they are squiggles. So if we're gonna apply what we know from these, alpha is definitely the bold straight lines, beta is definitely the dotted lines that are kind of curved, so zigzag, and gamma is squiggles. It's like a child writing, okay? As my teacher says, it's a child writing. Question number 5. Match each particle or ray to the corresponding track it leaves. As we did in the previous question, alpha is straight bold lines, beta is dotted zigzag lines, and gamma are a bunch of squiggles. Number 6. Where might the background radiation come from? So background radiation, it's the basic radiation, very minimal radiation that doesn't really affect us in our day-to-day lives. They usually come from the sun, so cosmic radiation, or radon gas. If they ask you for the percentage, it's 55%. And food and drink. Several pieces of thick aluminium, they do not give off radiation, and neither do blocks of lead. So here the only 3 answers are cosmic rays, radon gas, and food and drink. Number 7. The equation is detected radiation rate is equal to the total recorded rate minus average background rate. We're going to apply this in one of the questions. Now, select the expression that should be multiplied by the detected rate to get the total radiation emitted from a source. The total radiation emitted from a source, okay, whenever they ask you something, okay, in between the lines of the total radiation emitted from a source, and they give you the area, and they give you a radius, r, and they tell you it's multiplied by the detected rate, we used which equation? 4 pi r squared over a. To get into details, it's not necessary, but basically I will give a general idea. This here is something that will emit radiation. And then over here, we have the detector. So if it will detect, let me do a different color. If it will detect only this, okay, then this is only how much is being detected by the radioactive, by the detector, sorry. But in reality, the radioactive source is giving a circle, a much bigger circle. It's giving off this much. So to calculate it, they gave us this equation, 4 pi r squared over the area, okay? So we can find the total radiation emitted from the source. Again, why they asked us this? Because we have a source over here, and this is the detector. This is the only part being detected, but in reality, there is much more being emitted by this particle, which is the bigger circle. So that's why we need to multiply it by the detected rate. Now, question number 9. The actual radiation rate from a source is 27 becquerel. Okay. The radiation counter detects a radiation a radiation rate of 73 becquerel when placed near S. What's the background radiation? It was question number 7, I think. Yeah, detected radiation is equal to the total recorded rate minus average background rate. Then what do they need? They need the background rate, and we have the detected rate from the source, which is 27 becquerel, and we have the total radiation, which is 73. Okay, so we do the total radiation, 73, minus the detected coming from the source, 27, and we will get 46, I think. 46. Let me get my calculator to double check. So it was 73 minus 27. So yes, it is 46. Number 10. Which nuclei are unstable? Unstable nuclei can mean, we can find them by many things. First, either the ones that have a really high mass number, or something that can, like, how do you explain it? Something that can that can decay. Here's the word. Something that can decay. So, the ones with a really high mass number are usually this and this. Or another way of perceiving it is not only a high mass number or something that can decay, it's something that's not in its original mass number. For example, TH, the original mass number of TH, I don't know what it is, but it's definitely not this because it can decay. AT, it's definitely not this because it can decay. But for example, we know that iron, the original mass number of iron is 56. So it cannot decay because it's the original form. Okay? However, helium, we know that the original of helium, the mass number is not 8, it is 2 in the periodic table, but as we learned it, it is 4 and 2, the mass number is 4, so it can decay. And carbon, we know that the mass number of carbon is 12. So one way to say it is the ones that have a high mass number and they can decay. For example, 8,2He, it can decay into 4,2He. And here these two have really high really high mass numbers. Or you can check in the periodic table, if they will give it to us in the exam, which ones their mass number is not the one according to the periodic table, and then you choose. Question number 11. 16 grams of a radioactive material are isolated. After 15 hours, the radioactive material is measured to be 8 grams. So it halved. That means 15 hours is what? Our half-life, which we denote as this. So if they ever ask you for the half-life of something, you only have to find the original thing and see that after, for example, this case, 15 hours, it became half. So if it is halved from the original, then this time is what? The half-life. Number 12, a radioactive source R emits radiation into the space where electric field is maintained by two oppositely charged plates. So, what type of particles does the radiation source give out? If we notice here, we have negative and we have positive. We said those attracted to the negative are alpha. Why? Because alpha are positively charged. Those attracted to the positive are beta, because beta are negatively charged. And those that go towards B are gamma, because gamma has no charge. If we notice here, we have more readings towards A. It's the most, 300 becquerel. And we said the ones that go towards the negative are alpha particles. So it emits what? Alpha particles. Now, what material of the shield will ensure a narrow beam of radiation regardless of its source? So they want us to put here, from the source, a shield. They already put it for us. But they're telling us, in this shield, there needs to be something that will give the thinnest possible emission. Okay? It's gonna be lead, because lead can block alpha, it can block beta, and but it can block only a small amount of gamma. Or not a small amount, a considerable amount of gamma, but still a very narrow beam of radiation of gamma will pass. So we're gonna be using lead. Question number 13. So to resume, consider the tracks in a cloud chamber exposed to a certain radiation. First of all, when you look here, do you see straight bold lines or dotted lines or squiggles? If you notice, they are squiggles. So that means what? If they are squiggles, then it is gamma radiation. So the tracks in the cloud chamber are left by a condensed liquid. In the cloud chamber, there is a condensed liquid, okay? Or it's more of a gas, but then when you emit the particles, they will interact with the gas to make the condensed liquid. So the tracks are caused by a condensed liquid. And then the radiation that leads to the creation of such track is most likely a gamma radiation. We said why? Because they are squiggles. Okay? Now, which of the following is true about the presence and direction of the magnetic field in the cloud chamber? Since it's a gamma radiation, gamma, does it have a charge? No, it doesn't have a charge. So it cannot go neither positive nor negative. And in the magnetic field, it will not move because it's not going to be affected by it. So it's impossible to tell since this radiation is not affected by a magnetic field. So to recap here, we have bold, thick lines, straight, bold, and thick lines. They are what? Alpha. Alpha is positively charged, so it will go towards the negative. And in the magnetic field, it's gonna do an R shape. So in magnetic, it will do R shape. Okay? This is an electric field. This is for alpha. For beta now, they are what? Dotted lines. Okay? In the electric, okay, their charge is negative, so they will go towards the positive. In the magnetic, they will go towards the magnetic source, so it will be mainly a circle, kind of. Circle. I will write here towards magnet, because towards the magnet. And finally, we have the gamma. They are squiggles. Okay? And what about the squiggles? It has no charge and no mass. So that means it's not affected neither by the electric. So electric, we're going to put X. And magnetic, we're going to put X because it's not affected by any of them. Question number 14. Now, a radium source emits the 3 types of radiations in the presence of a magnetic field. The tracks formed in a cloud chamber by these radiations are shown below. So first of all, we have what? A magnetic field. If you remember from the previous question, we said in the magnetic field, the alpha will do an R shape, beta will do a circular almost shape, and it will go towards the magnetic field, towards magnet, and finally gamma is no effect. So track 1 we said is beta. Why? Because it's almost a circle. Track 2 is an R shape, kind of. It's going upwards and it's an R shape, so it is alpha. And track 3 is a straight line. It's not affected, so it is gamma. The direction of the magnetic field is actually into the plane of the picture, if I'm not mistaken, because look, if you notice, to which direction is the beta going? It's going into the plane of the picture. So this is our magnetic field. The other ones are out of the plane, definitely not, otherwise the beta would be bigger. To the left, it is to the left, but not to the left. It's going in the plane of the picture. It's not to the right and it's not downwards. So our answer is in the plane of the picture, because if you continue it, it will be inside of the picture. Number 15, a GM tube detects a radiation of 750 counts in 5 minutes. So the background radiation, whenever we have something like this, another way to find background radiation is what? You do the number of counts divided by the time in seconds. Okay, so first of all, let's change 5 minutes into seconds. That is 5 times 60, so 300 seconds. That means what? To find the background radiation, we do 750 over 300. What do we get? We are gonna get 2.5. Here we go. And finally, the major source for background radiation indoors is radon decay. We have to memorize this. Radon decay is 55%. It's the biggest source, or the most major source, for background radiation indoors. So our answer is radon. Let's submit and see. Alright, thank you guys for your time, and I hope you understood, and have a nice day.